students, welcome to Physics for Everyone classes. This is your Satish sir. In this video, I am dealing applications on the Lenz law, which means in various cases to find the direction of induced current. In the last video, we have learned about the Lenz law and its significance. If you are watching this video directly, I am suggesting you please watch the previous video to understand about the Lenz law, how the induced current is developed inside the coil. So let us start today's discussion how to find the direction of induced current in different cases. So we have the first case. Here I am taking a metallic ring. Here you can see this is the metallic ring, which is placed horizontally by some fixed support. And now take a bar magnet which is dropping along the geometrical axis of this metal ring. You can see here this magnet is taken at some height like this, and it is being dropping from there. As you know, any object is falling down with an acceleration due to gravity, due to gravitational force. But here, the acceleration attained by this magnet is somewhat different due to the induced current which is going to develop in this coil. Let us see how the acceleration is decreasing. So whenever this magnet is falling down, the flux generated by the North Pole passes through this coil. So as the magnet is approaching towards the coil, the magnetic flux passing through this coil also increases, which means North Pole is moving towards the face of the coil. The face of the coil comes as the North Pole, which we learned already in the previous videos. The induced current direction is, you can see, which is set in anti-clockwise direction. Now, the upper face of the coil comes as North Pole, and the lower face of the coil comes as the South Pole. Now, between these two same polarities, there will be an opposition to the motion of the magnet. With that, the acceleration is slightly decreases as compared to acceleration due to gravity. So, on this magnet, if you take the forces, for example, I am taking here, this is the mass of the magnet is m. In downward direction, there will be a gravitational force mg. In the opposite direction, there exists an opposition force due to repulsion between the same polarities. We can write here opposition force which is F, or you can write it as FO, which is the opposition force. So on this magnet there will be two forces. One is gravitational force in the downward direction, and second is the opposition force due to this current carrying coil on the bar magnet. So with these two forces, the net force acting will be in the downward direction, or we can say it as a resultant force, F. So let us write the Newton's second law. For this case, it comes as Fr, net force is equal to downward force which is mg minus upward force which is opposition force F naught. F1 we can write it as m into E according to Newton's second law. Any net force is equal to mass of the body into its acceleration. that is equal to mg minus f naught, or we can write A is equal to G minus F naught divided by M. You can see this M is taken to that side, M and M get cancelled. The second term it comes as F naught by M. So altogether you got the acceleration of the magnet which is coming in downward direction or towards the face of the coil is given as A is equal to G minus F naught by M. If the opposition force is 0, F naught is 0, there is no opposition, there is no induced current, then A is directly equal to G. But here we got, due to induced current and induced magnetic flux, there exists always an opposition according to Lenz law. So this is the case, you got the acceleration which is less than the acceleration due to gravity. How we can say less than? Because we are detecting some factor F naught by M from G minus F naught by M. So you can write A which is less than G. So what is the summary? If any bar magnet which is dropping on the top of the metallic ring, it will come down, but due to opposition force caused by the induced current, the acceleration of the bar magnet is less than the acceleration due to gravity. This is a very important result. Suppose as the time progresses, this bar magnet will pass through this metallic ring. In one particular time, you will get the magnet is below the metallic ring, like this. There you can see the south pole is closer to the bottom face of the coil, and which is moving away from the coil. So as the south pole is moving away, the lower face of the coil should come as north pole in order to oppose its motion. As the south pole is going away, to oppose the motion, the lower face of the coil must come as a north pole to attract this south pole. Then only the motion of the magnet is being restricted. So initially it was south pole. Now this one is changed as north pole, as this magnet is crossing this metallic ring. And the upper face of the coil, initially it was north pole. Now it comes as a south pole. So what you can say, as the magnet is above the metallic ring, when it is approaching the metallic ring, there the upper face of the coil is north pole and the lower face of the coil is the south pole. Once the magnet crosses this metallic ring, the direction of induced current is reversed. You can see here, it comes in the clockwise direction to attract this magnet. The lower face becomes as the north pole and the upper face now becomes as the south pole. So in this way, when the magnet is crossing the metallic ring, initially the upper face of the coil is north pole and the lower face of the coil is south pole. Once it crosses the metallic ring, the polarities are reversed due to the change in the direction of the induced current in the coil. So once the induced current is being set in a clockwise direction, the upper face comes south pole and the lower face comes as the north pole. Is it clear? Right. Now in the second case, if you are seeing the same metallic ring, but it is some part is being removed, we can call it as the cut ring. The remaining things are almost similar. That is, we are dropping again here the bar magnet along the geometrical axis, and this is falling down. Will you get opposition in this case? No. The reason is that when the circuit is not closed, This is the very basic point that to flow the current, the circuit has to be closed. But here the circuit is open. Due to that, the induced current is not developed here. But still, you will get the induced EMF due to there will be the change in the magnetic flux. You can see as the magnet is coming down, this magnetic flux passing through the coil gradually increases. With that, you can see the induced current is being set, but we are not detecting any current. As you got that point? So how you say that there will be a potential difference between these two? If suppose the induced current is set, it will be in the anti-clockwise direction. It will be in the anti-clockwise direction. Due to that, the electrons will move in the opposite direction. As you know, the motion of electrons are always opposite to the direction of conventional current. You can see the electrons are supposed to move from the point A towards the point B. But here, this part is removed. Due to that, the circuit is not closed. How much is current in the circuit? Which is equal to 0. But as the electrons are starting from the point A or losing some electrons from that point, we can take this point comes as the positive potential point, higher potential point, where the electrons are shifted towards the point B, where it comes as the lower potential point. We can take it as the negative. So in this way, you will get the potential difference between the points A and B, but there will be no induced current. But still I am taking the direction, you can understand. If suppose, if you take the complete metallic ring, then we can say the current induced in the coil is in the anti-clockwise direction. But here, the current is how much? Induced current is 0 because we are taking it as the cut ring. So induced current is 0, induced EMF is existed. It is being like a open circuit. If the circuit is closed, you will get the induced current. Here we have the second case to find the direction of the induced current. Here on the board, I am taking the two identical metallic rings, A and B. Identical in the sense both have the same nature and also the same dimensions. But the ring A, which is kept at temperature 20 degrees Celsius, and the ring B is kept at 50 degrees Celsius. There you can see the temperature of A, which is less than the temperature of B. Now, the same thing, the bar magnet is dropping along the geometrical axis of the bar magnet. There you can see. Here, the question is that in which case the bar magnet falls with more acceleration. We know the direction of induced current. It will be along the anti-clockwise direction in both the cases, as the north pole is coming towards the coils. So what is the direction of induced current? Yes, it is anti-clockwise direction. We already seen. Let us take anti-clockwise direction in both the coils. The upper face of the coil, yes, it is north pole, and the lower face of the coil is the south pole. Here also same. The upper face is north and the lower face is the south in order to oppose the bar magnet. Now, with respect to temperature, which magnet falls faster? Is it in the case of A or the case of the B? Now, what is the relation between the temperature and the induced current in the coil? We need to take the relations from there, the resistance and temperature. We studied in current electricity for all metals, almost all metals, we take the relation resistance is proportional to the temperature. As the temperature increases for the metals, resistance also increases. You see, the temperature of A, metal A, which is less than the temperature of the metal A. So with this relation, we can write direct relation, the resistance of A, which is less than the resistance of B. So in A, as the resistance is smaller or less, induced current developed in this coil is more. So what we can say? The induced current which is created due to the change in magnetic flux is more as compared to the induced current in the metallic ring B. So we can write here induced current in A, which is more than induced current in the metallic ring B. So we see temperature of A is less than B. With this relation for metals, you can write resistance of A is less than the resistance of B. As you know, current and resistance both are inversely proportional by Ohm's law. We will get induced current in the coil A is more than the induced current in the coil B. So what we can say, as the induced current is more, you will get the more opposition on the bar magnet, the more opposition force. So directly we can write the opposition force acting on the bar magnet A, which is more as compared to the opposition acting on this bar magnet due to metallic ring B. As the opposition is more, what you can say about the acceleration of the magnet, which was given in the earlier case. Acceleration of A is equal to G minus F naught of A divided by M. And acceleration of B, which is given as AB is equal to G minus F naught of B divided by M. You can see F naught of A, which is greater than F naught of B. So what we can say about the acceleration of A and B, as this factor which is more as compared to this one, you will get the acceleration of A which is less than the acceleration of B. Means the bar magnet in the second case, which is moving down with more velocity, or it takes less time to reach the metallic ring. Now we have got a third case to find the direction of induced current. There you can see. Here I am taking a circular coil which is placed parallel to the plane of the board, and below it I am taking a current carrying conductor. You can see here this current carrying conductor which is placed in the same plane of the coil. Now as this current is increasing, assume that the current passing through this conductor is increasing. With that, the magnetic flux linked with this coil also increases. Initially, we need to find in which direction the magnetic lines of force are passing through this coil. For that, we need to use the right hand thumb rule to find the direction of magnetic field. It is very simple. You see, for example, this is the current carrying conductor. I am taking into my hand in this way. So as the current is moving in the upward direction, you can see the current is moving in the upward direction. The curl of the fingers gives the direction of magnetic field. If you look from the top side, for to me, the direction of magnetic field is anti-clockwise direction. The same current which is moving in the downward direction, the curl of the fingers is set in clockwise direction. Means the direction of magnetic field is clockwise. The same you can apply here to find the direction of magnetic field. Imagine this is like a current carrying conductor. Take in your hand like this. The thumb represents the direction of the current. The curl of the fingers gives the direction of magnetic field. And this plane is on the left side of this conductor. You can see it is on the left side. There we have a rule to easily find out the direction of magnetic field, which is L out. If the coil is on left side of the current carrying conductor, the magnetic field will come out of the coil, which means in this direction. If this coil is kept on the right side, there you will get RIN, which means if the coil is on right side, there you will get the magnetic field direction is into the board. So directly you can draw here some magnetic lines of force with this L out on the left side. The magnetic field is coming in outward direction, out of the board. The symbol is that out of the board. We can use the symbol is dot. Into the board, you can use the symbol cross. Here it is out of the board. So I am taking the symbol of magnetic lines of forces are coming outside in this manner. So we can take so many like this. So the symbol represents the direction of magnetic lines of force due to this current carrying conductor. So what will happen? As the current increases, this magnetic lines of force or magnetic flux also increases in the outward direction. And what is Lenz's law? The induced current will set in this coil in such a way to oppose the change. Here the flux is increasing, so the opposition to the increasing is decreasing, which means here in this coil current is induced, which will create its own induced magnetic field opposite to this direction. That means I can use the symbol cross, induced magnetic field into the board which opposes the outside flux. So when the magnetic field is into the board, the curl of the fingers is in which direction? This is clockwise direction. So there you can see the direction of the induced current we got here is clockwise. To set the induced flux into the board which is opposing the initial outward flux due to current carrying conductor. The same coil, if it is taking in the downward direction or the below of this current carrying conductor. So firstly identify the magnetic lines of force due to current carrying conductor. It is on the right side of the current carrying conductor. Then we have a rule on the right side, the magnetic lines of force are into the board. So into you can use the symbolic representation is the symbol is cross. In this manner you can take the magnetic lines of force due to current carrying conductor is into the board, which is increasing due to increase in current. So here also the flux passing through this coil is increasing, which means induced current will be developed. In which direction? So this induced current is oriented in such a way to oppose this, the increase in flux, which means we need to take the magnetic lines of force which are few in the outward direction. So you can see some field lines, if I am taking an outward direction, there you will get the induced current direction is in the anti-clockwise direction in this way. So if the induced current is in anti-clockwise, the induced magnetic flux is in the outward direction, which opposes the initial external magnetic flux due to current carrying conductor. So like this, if you will get many more cases to find the induced current direction, the rule is very simple. We to take the basic definition of the Lenz law. It always, the induced current always set in a coil in such a way that it opposes the cause that produces it. But with the help of Lenz law, we can find the direction of induced current very easily. So thank you very much. If you are watching this channel for the first time, please subscribe and support the channel. Thank you very much.